Hi, I'm Mark Barsemian. In this video, I'll be discussing direct proof and counterexample methods again, as in the last two videos. Today we'll be adding an additional mathematical definition, that of rational numbers. Recall that in the first two sections of Chapter 4, our introduction to proofs used only the simplest of mathematically defined terms: even and odd numbers, composite and prime numbers, and consecutive integers. So today's video, with its introduction to rational numbers, is a significant jump in sophistication. In addition to having the defined term rational numbers, it will sometimes be useful to have another defined term that's the term irrational numbers, and also to use the zero product property of the real numbers. The definitions and the statement of the property will follow below. So the definition of rational numbers is this: to say that R is a rational number means this: R is a real number, and this existential statement: there exists A, B that are integers such that R equals A over B. Now, I'm going to remark on the difference between this presentation of the definition and the book's presentation. This equation, R equals A over B, involves real number equality. It can only be true if the things on both sides of the equal sign are real numbers. That means that the denominator B has to not be zero. That requirement is not explicitly stated in my definition, but it does not need to be because it's implied. The only way that this equation can be true is when B is not equal to zero. The book's definition does explicitly state that. Some notation: the symbol Q, boldface, denotes the set of rational numbers. Notice that the set of rational numbers is a subset of the set of real numbers because every rational number is a real number, one with extra qualifications. And a related definition is that of an irrational number. That just simply means that the number R is a real number and R is not rational. Now, there is no commonly used symbol for the set of irrational numbers, but we can express it as a difference. So the set of all irrational numbers is the set of all real numbers minus the set of rational numbers. The zero product property of real numbers says that if a product of two real numbers is zero, then at least one of the real numbers is zero. That's a conditional statement, so it has a contrapositive that means the same thing. The contrapositive says if two real numbers are both non-zero, then their product is non-zero. Both of those sentences are stated informally. If we state them formally, they look like this: for all real numbers A and B, if A times B equals 0, then A equals 0 or B equals 0. That's the formal version of the zero product property. The formal version of the contrapositive is this: for all real numbers A and B, if A is not 0 and B is not 0, then A times B is not 0. For our first example, we're presented with three numbers that are known to be rational, and the job is to write each of these as a ratio of integers. Notice that this first one, question A, is a terminating decimal. And there's, I guess, a trick. It's not really terribly hard to understand, though, so it almost doesn't deserve to be called a trick. We can just write this as 5,678 divided by 1,000. Okay, let's go on to question B. Now this number is a repeating decimal. Now there's a little bit more subtle trick in this problem. Really, two tricks. The first trick is to introduce a letter that represents this number. So that doesn't seem terribly profound, But the next step is a trick. So if I multiply my number r by 1000, it moves the decimal 3 places to the right, but then the repeating part after the decimal place looks just like it did in the original expression for r. So here's another trick. When I subtract r from 1000r, all of this stuff to the right of the decimal lines up perfectly and cancels. So I end up with, notice that the difference is an integer. And notice that the left side can be rewritten as 999r. So if I divide both sides by 999, I get this. And there's our result. R is expressed as a ratio of integers. Now what about question C? We have a repeating decimal, but it does not repeat immediately. It repeats after 2 places. Then it starts the repeating pattern. How do we express that as a ratio of 2 integers? Well, we'll do that on the next page. So we have a repeating decimal, but the pattern does not start right away. How do we attack this? Well, we do what we did in the previous problem. We introduce a letter r to represent the number. And it turns out we do a similar trick of multiplying r by a big enough number that the decimal place will move, but we'll have to do this twice. So 100r is this new expression where the repeating pattern starts immediately after the decimal. Now if I multiply this new thing by 1000, I get another decimal with the same repeating pattern to the right of the decimal place. And I do the same trick as before. I subtract one from the other. The result of the subtraction is an integer. So we have an equation. The left side is 99,900r, and the right side is that integer. So that means that r is a ratio of integers. That's the end of that example. Let's go on to the next one. In example 2, we let s be this statement. The square of any rational number is rational. So question A is to write the formal version of this statement s. So the formal version is, for all r that are rational numbers, r squared is a rational number. Now let's rewrite that formal version as a universal conditional statement. That is to think about splitting the qualifications of that domain into 2 qualifications and putting some of those qualifications into the hypothesis of a conditional statement. So there's a universal conditional statement. Remember, I said I was going to split these qualifications up into 2 parts of qualifications. Put some in the domain and some in the hypothesis. But this is a little bit weird because this requirement that x be a rational number includes the requirement that x has to be real. Remember, the definition of rational numbers includes the requirement that the number be a real number and that it can be expressed as a ratio. So it might seem weird to have this put in front if I'm also going to have this in my hypothesis. But you'll see why this is useful in a few minutes. Notice one more thing. In question A, I use the letter r for my variable because I'm going to be talking about rational numbers, the only numbers I'm going to be talking about in question A. So I might as well use a common symbol for rational numbers, the little r, which makes you think of ratio. But in question B, I'm starting out by talking about real numbers that might or might not be rational. So I use the letter x, which is a common variable that makes us think of real numbers. Now in question C, we're going to prove statement S, so it's going to be useful to have a copy of this statement on the next page. So I'm going to copy this, put it on the next page, and when we scroll down, we'll find it there. So here we are in question C, and the job is to prove statement S. And we see we've got statement S here copied from the previous page. So remember how we prove something like this. We have to put the description of the domain and the hypothesis all in statement 1. So in other words, we start the proof by saying, suppose x is a real number and that x is rational. And remember how this proof has to end. It has to end with the conclusion statement. So that's got to be at the very end. So there's our proof structure, our proof frame. And remember, that frame style is called the direct proof. So we know that our proof has to begin with statement 1 and end with this statement down here, which is a statement of the conclusion. So that is inevitable. Now there's more stuff that's inevitable. Notice that this is a defined term. So we have no choice about what's going to have to come in statement 2. So we have no choice. We have a defined term, so we have to follow that up with a statement that is the unpacking of that definition. Now let's look ahead to the end of the proof. The end of the proof has a defined expression as well. To say that x squared is an element of the rational numbers, that's a defined term. So we have no choice how we're going to have to get to this last statement. The only way to get to here is to have previously had this statement. So we're going to have to get to that statement before we can get to the final statement. When we finally do get to the final statement, the justification for it is going to be by the previous statement and the definition of rational. So notice, here we're using the definition of rational again, but we're packing up the definition. We're taking this sentence, which has a lot of words in it, and we're restating it using the abbreviated terminology that x squared is rational. All right, now how do we bridge this big gap in the middle of the proof? Well, notice that we want to end with this equation. We don't know where we're going to get our c and our d, but we do know where we can get our x squared. We've got x already appearing in the proof. So let's go back up and resume with a statement 3 where we just simply build x squared. That is, we want to have this equation by the time we get down here to the end of the proof. So let's build the left side of the equation. Now look, we have an equation that says x squared equals a squared over b squared. We want to have an equation that says x squared equals c over d. So it's clear what we should do now. We should introduce letters c and d that will work. And we should say something more about c and d. Notice that we do need to say very clearly that c is an integer. And we also need to say something else. We want d to be qualified to be in the denominator of a ratio, and it has to equal some real number. So d is going to need to be non-zero. How do we know that d is not 0? Well, let's just say the words that d is not 0. Now, how can we justify that? Well, notice that if we go back to this equation is true, and that tells us that b must not be 0. So we can use that in our justification of our statement 4. So from statement 3, we know that that should be statement 2. From statement 2, we know that B is not 0. And then from the zero product property, we know that B times B is also not 0. So there we actually have all we need. We can number the red step, and we can number the blue step at the end of the proof. And furthermore, we know that in the blue step at the end of the proof, the justification is by step 5. And there's our proof. So notice again the approach to proving by identifying the proof structure. We identified the direct proof structure that we are going to have to use, and then we identified that we are going to have the green statement and the red statement to deal with the definitions that we were using in the statements of the blue frame. Let's go on. Question D says to write the formal versions of the contrapositive, converse, and inverse of statement S. Now I've put here a copy of statement S that we had on the previous page. So notice that statement S is a universal conditional statement. So its contrapositive is for all real numbers x, if x squared is not rational, then x is not rational. Notice that's the form if not B, then not A. The original statement S was if A, then B. What about the converse of S? The converse of S is for all x in R, if B, then A. That is for all real numbers x, if x squared is rational, then x is rational. The inverse? The inverse of S is of the form if not A, then not B. So for all real numbers x, if x is not rational, then x squared is not rational. Question E says, which of the statements in D are true and which are false? Let's go back up and look at these. We have the contrapositive of S, the converse of S, and the inverse of S. Well, remember that the contrapositive of S is logically equivalent to S. So these two statements mean the same thing. And we've proven that S is true. So the contrapositive of S is automatically true. But the converse of S is not logically equivalent to S. The fact that S is true does not tell us anything about whether its converse is true. Remember from previous chapters that we've seen examples where an original conditional statement was true and its converse was true. We've also seen examples where an original conditional statement was true and its converse was false. So we can't say right off the bat whether the converse of S is going to be true or false. Let's go up and have a look at it. The converse says, for all real numbers x, if x squared is rational, then x is rational. And remember that that is logically equivalent to the inverse of S. The inverse says for all real numbers x, if x is not rational, then x squared is not rational. Now, is that true or false? Well, I don't want to get bogged down here because we're going to study this in coming weeks, but I want to just bring up an example. Notice this is a universal statement. If we were going to try to prove that converse was true or that the inverse was true, we would have to come up with a general proof. But if we suspect that these statements are false, all we have to do to prove that they're false is come up with an example. a counterexample that proves that these statements are false. Well, let's think about one special number. Square root of 2. Square root of 2 is a real number, and it's a famous fact that we'll prove in coming weeks that square root of 2 is not rational. Square root of 2 is irrational. But also note that if I square the square root of 2, I get 2, which is rational. So we have an example of a real number x such that x is not rational and x squared is rational. Let me turn that around. So we have an example of a real number x such that x squared is rational and x is not rational. So that example is a counterexample that proves the converse is false. The converse says for all real numbers, if x squared is rational, then x is rational. We have an example of a real number where x squared is rational, but x is not rational. So our conclusion is the converse is false. And again, since the inverse of s is logically equivalent to the converse of s, the inverse of s is also false. All right, that's the end of that example. Example 3. Let s be this statement. The difference of any two rational numbers is rational. So question A is to write the formal version of s. Well, that means to express it in symbols using symbols for quantifiers. Here's one way of doing it. So notice I have a quantifier that says for any two rational numbers, and then the predicate says the difference of those two rationals is rational. Let's write this in a universal conditional form. So there you see that I've broken off part of the qualifications mentioned in the domain description, and I've put them in front. X and Y are real numbers. And then in the hypothesis, I put the rest of the qualifications, X and Y, are rational numbers. Notice that in the original statement, I used letters R and Q because those are commonly used letters for rational numbers. But in the universal conditional form, I used letters X and Y because at the beginning of this statement, all we know about X and Y is that they are real numbers. So I wanted to use letters that are commonly used to denote real numbers. Now, in the next part of this question, we're going to have to decide whether this statement is true or false. So I'm going to copy this statement that we've written here in symbols and put it on the next page, and we'll find it there when we scroll down. So here we are, question C. Prove or disprove statement S. So we have to decide whether we think it's true or false. And if it's false, we have to suggest a change that would make it true. All right, well, statement S says for all real numbers X and Y, if both of those numbers are rational, then their difference is rational. Well, this is true, and I think it's probably clear enough to you that it is true. So I think we'll just embark on a proof without discussing, without me trying to convince you that it's true. So let's just start with the proof. So remember how the proof is going to start. It's going to be a direct proof structure. So that means statement 1 we have no choice about. Statement 1 is going to have to take care of the description of the domain and the hypothesis. So in other words, we let X and Y be so statement 1 is where we introduce generic particular elements. So letters x and y that have the qualifications mentioned in the description of the domain and in the description of the hypothesis. Remember that the direct proof method is the method of generalizing from the generic particular element. And we know how this proof is going to have to end. It's going to have to end with the statement that's the conclusion. All right, well, where do we go from here? Same thing we've done before. Observe that one of the things mentioned in statement 1 uses a defined term. Rational numbers is a defined term. So we have no choice but to follow statement 1 up with a new statement that expresses that in less abbreviated form. So this green statement is by statement 1 and the definition of rational. And let's look forward to the end of the proof. This last statement of the proof has a defined term, rational. So we know how this proof is going to have to end, and we also know how the second to the last statement is going to have to go. And furthermore, if that's the second to the last step, we know that the justification for the last step is going to have to be the definition of rational. Now, remember that there's an issue of ratios of integers needing to have non-zero denominators in order to actually define real numbers. So I'm going to do something different in this proof that I didn't do in the last proof. I'm going to actually put in an explicit line in statement 3 that says b and d are not 0. So the reason we know that they're not 0 is because a over b and c over d are real numbers. All right, now where do we go from here? Well, let's look forward. We want to get to this equation. I don't know how we're going to get the right side of that equation, but the left side of that equation we can build right now. So let's just start by building the left side of that equation and see where that takes us. That'll be our step 4. Now look what happened here. We now have an equation that says x minus y equals this ratio. And look, we want to have an equation that says x minus y equals e over f. So it's clear that we need to introduce our e and our f at this point. And let's right away say without any other explanation necessary that those are both integers. Because the basic property of integers is that if you multiply two integers together, you get an integer, and if you subtract two integers, you get an integer. That's prerequisite stuff for this course, so we don't really have to explain that stuff. But we do need to say that f is not 0, and that's significant, so that is going to get its own line. So the reason we know that f is not 0 is by this statement 3, b and d are not 0, and so their product is not 0 by the zero product property. So that gets its own line in the proof. Now look, we're ready to go with renumbering our red statement. This red statement is going to be statement 7. The final blue statement is going to be statement 8, and it's going to be justified by statement 7. There's our proof. Let's go on to the next example. Statement S in this example is the quotient of any two rational numbers is rational. So question A says to write the formal version of that. So the formal version is for all rational numbers q and r, q over r is rational. Let's rewrite this in the form of a universal conditional statement. Now in the next question, we're going to be asked if this is true or false. So I'm going to put a copy of this on the next page. We'll find it when we scroll down. So here we go. Here's statement S. We have to prove or disprove this. For all real numbers x and y, if x and y are rational, then x over y is rational. Well, let's explore a bit. So notice that we just start looking at some samples of x's and y's that are integers. In a lot of cases, when we take the ratio, we get something which represents a real number. So 3/5 is a real number, so 3/5 is rational. 5/3 is a real number, so 5/3 is a rational number. 0/1 is a real number. It's the real number 0. So 0 qualifies as a rational number. The ratio 0/1 qualifies as a rational number. But this expression does not represent a real number. It's a ratio of integers, but it does not represent a real number. So it's undefined. It's not a rational number. It's not irrational either, because it has to be a real number to qualify as an irrational. It's not even a real number. It's not a number at all. So S is false. And we should be very clear. We should present the counterexample. And we should really hit the reader over the head with it and point out very clearly why it is a counterexample. So there's our presentation of the counterexample. Now what about this? If S is false, suggest a change that would make it true. Now notice that my sample x's and y's, I was supposed to explore by looking at x's and y's that were rational numbers. I only looked at x's and y's that were integers though. What would have happened if we had used x's and y's that were rational numbers that were not integers? Well, we would have observed the same sort of thing. The only case that would have caused a problem would be the case where y was 0, because we would have ended up with a 0 in the denominator. So if we want to think about how to suggest a change that would make S true, well, let's do that on the next page. So there's our statement S, which is a false statement. And we need to think about how we could fix it so it's true. So let's call our fixed statement the improved statement S. So the new improved statement S would be, for all real numbers x and y, if x and y are rational and y is not 0, then x over y is rational. Now, it's worth thinking a little bit why this is true. We don't have to do a full proof, but let's think about why this is true. So suppose x and y are rational and y is not 0. So if we have rational numbers x and y, and we also know that y is not 0, we know that we can express x and y as ratios. They're rational numbers. And we know a lot of stuff. We know that the denominators have to not be 0 because x and y exist as real numbers. But we also know that this numerator, c, is not 0. And that's because y is not 0. So now look what happens when we build the ratio. We get this ratio AD over BC, and we know that the denominator BC is not 0 because B and C are each not 0. So I didn't write this up as a complete proof using the clear proof structure, but it works pretty well as something that convinces us why this is believable. So that's the end of this example, and that's the end of the video. Thank you.